You've asked it to write an essay, summarize a book, or maybe even craft a hilarious meme caption. And boom! Out comes text so coherent, so human-like, it feels almost magical. We're talking about large language models, or LLMs, the technology powering tools like Chat GPT. They seem to understand us, learn from us, and even think like us. But here's the mind-bending truth. An LLM doesn't think at all, not in the way you or I do. It's not a conscious entity, plotting world domination, or even having an existential crisis. It is, at its core, a machine built on mathematics. So if it doesn't think, how does it conjure up those perfectly worded responses? How does it predict the next word with such eerie accuracy? Today, GENSHIFT is cracking open that black box. We're going on a journey inside the digital mind of an LLM to reveal its surprising secret. Get ready to have your understanding of AI fundamentally shifted. Hit that subscribe button now to join us in decoding the technologies shaping our world. One, the predictive machine. LLMs don't understand, they predict. So what is the secret? If an LLM isn't thinking, what is it doing? The answer is both simpler and more complex than you might imagine. Fundamentally, an LLM is a prediction engine. That's it. Its only job is to look at a sequence of text and calculate, with stunning accuracy, what word is most likely to come next. Think of the predictive text feature on your phone, but scaled up to an almost unimaginable degree. When you type, "I'll meet you at the," your phone suggests library, park, or cafe because it has learned common patterns from your typing history and general language use. Now imagine a system that hasn't just learned from you, but has been trained on a colossal dataset of text and code from the internet. Trillions of words from books, articles, websites, and forum discussions. When this supercharged system sees the phrase, "Mary had a little," it doesn't access a memory of a nursery rhyme. Instead, it performs a massive statistical calculation and determines that, out of all the possible words in its vocabulary, the word lamb has the highest probability of appearing next based on the patterns it observed during its training. It then appends lamb to the sentence and repeats the process, predicting the next word and the next and the next, generating entire paragraphs that feel remarkably coherent. This predictive power is so convincing that it triggers a deep-seated cognitive bias in all of us: anthropomorphism. We are biologically and socially wired to attribute human-like intentions, thoughts, and emotions to non-human things, especially when they exhibit complex human-like behaviors. When an LLM generates text that is empathetic, witty, or insightful, our brains instinctively want to believe there is a mind behind the words. This psychological shortcut is why these tools can feel both awe-inspiring and, for many, a source of anxiety. Surveys show that while Gen Z uses AI tools extensively, many also fear that AI will eliminate jobs and harbor a general skepticism about the technology's impact. This fear is often rooted in the perception of AI as a competing intelligence. But by understanding that the intelligence we perceive is the output of a probabilistic, pattern-matching machine, we can begin to see the technology more clearly. It's not a rival mind. It's a powerful and sophisticated mathematical tool that excels at one specific task: next word prediction. 2. Tokens and embeddings, the language of the LLM. Understanding that LLMs are predictive machines is the first step. The next question is, how does a machine that only understands numbers process something as nuanced as human language? The answer lies in a two-step process of translation that turns words into pure mathematics. The first step is called tokenization. Before an LLM can even begin to process your prompt, it shatters the text into smaller, manageable pieces called tokens. Imagine your sentence being fed into a digital shredder. Out come individual words, parts of words like prefixes or suffixes, and even punctuation, each as a distinct token. The sentence "LLMs don't think" might be broken down into tokens like LLM, S, Don, A, T, think. This process allows the model to handle a vast vocabulary and understand grammatical structures more effectively, as it learns the meaning of not just whole words, but their parts as well. Once the text is broken into these tokens, the real magic begins. Each token is converted into a long list of numbers called an embedding. This is the crucial moment where language becomes math. An embedding is essentially a numerical representation, a vector that captures the semantic essence of a token, but it's more than just a code. The best way to visualize this is to imagine a vast, multidimensional galaxy of meaning. In this vector space, every single token has a specific coordinate. Tokens with similar meanings are clustered together. The token for cat would be located very close to the tokens for kitten and feline, while being incredibly far from tokens like car, planet, or the democracy. This proximity equals meaning principle is the foundation of how an LLM understands relationships. But it gets even more profound. The relationships between tokens also become mathematical vectors. The most famous example of this is the equation vector king, vector man, plus vector woman, vector queen. The model has learned a gender relationship vector and a royalty concept vector. It doesn't know what a king or queen is in the human sense, but it has mapped their relationship in this geometric space of meaning. It can do the same for verb tenses, country capital pairs, and countless other abstract relationships. So when an LLM processes your prompt, it's not reading words. It's navigating through this incredibly complex geometric map of human language, using the positions and trajectories of these numerical vectors to calculate the most probable path forward. Language for an LLM is not a collection of words, but a universe of points and vectors. 3. The transformer, the architecture of attention. We now know that an LLM turns words into numerical coordinates in a vast semantic galaxy. But what is the engine that navigates this galaxy? That engine is a revolutionary neural network design called the transformer architecture. First introduced in a 2017 paper titled "Attention is All You Need," the transformer is the brain behind virtually all modern LLMs, from GPT to Gemini. While the full architecture is complex, its superpower can be distilled to one breakthrough concept: the attention mechanism. This is what gives an LLM the ability to understand context by weighing which words in a sentence matter most when predicting the next one. Imagine every word in a sentence is a person standing in a room, each trying to understand their role in the conversation. Take the sentence. The trophy would not fit in the brown suitcase because it was too big. For older AI systems, the word "it" created confusion. Was it the trophy or the suitcase? The attention mechanism solves this by letting it essentially raise its hand and issue a query. I need to refer to something. Which of you is most relevant to too big? Each word responds with its own data, called keys, and the model calculates which words should receive the most attention. The model then uses this weighted attention to form a final value that guides its next prediction. In this case, the model correctly focuses on trophy as being too big. So when we say attention is all you need, we're really saying this. Attention is how an LLM mathematically focuses on meaning. It's how the model builds a mental map of context and relationships. And it's the engine that transforms random text generation into fluent, meaningful thought. In response, every other word in the sentence that came before it holds up a sign describing its identity. This is the key. The word trophy holds up a key that says, I am a singular noun. The word suitcase holds up a key that says, I am also a singular noun. The model then compares the query from it to the keys from all the other words. By analyzing the full context, especially the phrase too big, the model calculates that trophy is a more likely antecedent. It assigns a higher attention score to trophy than to suitcase. It's like a spotlight shining brightest on the most relevant word. Finally, the word with the highest attention score, trophy, is asked to share its full meaning. This is the value. The rich semantic embedding of trophy is then passed along to the word it, informing its context. The model now knows that it refers to the trophy. By repeating this process of asking queries, checking keys, and passing values for every word in the sequence, the transformer builds a deeply interconnected, dynamic understanding of the entire text. It's not just reading words in order. It's creating a complex web of relationships, allowing it to grasp nuance, resolve ambiguity, and generate text that feels remarkably context-aware. This is how it knows what it means. 4. Beyond prediction, limitations and responsible use. Now that we've peered inside the black box and seen the gears of prediction, tokens, and attention, we can finally understand not just the LLM's strengths, but also its critical flaws. The very mechanisms that make LLMs so powerful are also the source of their biggest limitations. Understanding these limitations is the key to moving from a passive user to an intelligent, critical collaborator with AI. First, there's the problem of hallucinations. Because an LLM is designed only to generate the most statistically plausible sequence of tokens, not to state verified facts, it can confidently make things up. If a user asks for legal cases supporting a certain argument, and the model's training data doesn't contain enough relevant examples, it won't say, "I don't know." Instead, its predictive engine will assemble a response that looks like a list of real legal cases, complete with fake case names and citations, because that is the most probable structure for such an answer. This is not lying. It's a byproduct of a system optimized for coherence, not truth. Second, LLMs inherit and can amplify bias. The models are trained on a massive snapshot of the internet, which is filled with humanity's collective biases and stereotypes. If the training data repeatedly associates certain job roles with men and others with women, or links certain racial groups to stereotypes, the model will learn these patterns as statistical truths. Even with extensive fine-tuning to reduce explicit bias, subtle implicit biases can remain, influencing everything from hiring recommendations to the tone of generated text. Finally, LLMs lack true common sense. They have learned relationships between words from text, but they have no lived experience, no physical understanding of the world. An LLM can tell you that you can't fit a trophy in a suitcase if it's too big, but it can't reason about why. This lack of embodied knowledge means it can fail at simple reasoning tasks that a 7-year-old would find obvious. These limitations aren't bugs to be fixed, they are inherent features of the current technology. This means that using AI responsibly falls on us. First, verify everything. Treat LLM output like a starting point from a brilliant but sometimes unreliable intern. Always cross-check important facts, figures, and sources using reputable academic databases, news outlets, or expert websites. Second, master the art of the prompt. Communicating with an LLM is a skill. Be specific, provide context, and structure your questions clearly to guide the model toward a more accurate and useful response. Third, be mindful of ethics. Remember that the data you input can be used for training, so avoid sharing sensitive personal or proprietary information. Understanding these rules of engagement is the foundation of AI literacy, a critical skill for navigating our future. Conclusion. So, the black box isn't so black after all. Inside, there isn't a thinking mind, but a breathtakingly complex engine of statistical prediction. It's a machine that translates our language into a galaxy of numbers and navigates it using a sophisticated web of attention. It's not magic, it's math. And knowing this is a superpower. It allows you to harness the incredible capabilities of these tools while sidestepping their inherent flaws. It replaces fear with understanding and transforms you from a simple user into a savvy operator. This knowledge is the key to collaborating with AI effectively, ethically, and intelligently. So, what are your thoughts after peering inside the LLM's black box? Does knowing how it thinks change how you'll interact with AI? Share your insights and questions in the comments below. We'd love to hear from you. And if you're ready to keep unraveling the mysteries of tomorrow's tech, subscribe to GENSHIFT for more deep dives that empower your digital future.